Greetings everyone and welcome to the 8th video in this 10 video series. My name is Vyom Khanna and I am thrilled to be with you all today. In the previous video, I hope you learned a great deal about LCD panels and how you can display all sorts of information on them. In the previous video, we explored not only the software but also the hardware of LCDs and how you can integrate them into your projects. Over the remaining videos, we will delve deep into concepts like 3D printing, robots, NodeMCU, soldering, and most importantly, real-life applications. Today, we are on the 8th video in this series, so let's keep on going. This video will explore NodeMCU, databases, and other cool components, along with how we can integrate them into our projects so that we can achieve more. So, let's get started with what the NodeMCU actually is. The NodeMCU, which full form is Node Microcontroller Unit, is an open source software and hardware development environment built around an inexpensive system on a chip called the ESP8266. The ESP8266, designed and manufactured by Espressif Systems, contains the crucial elements of a computer: CPU, RAM, networking, and even a modern operating system and an SDK. That makes it an excellent choice for Internet of Things projects of all kinds. However, as a chip, the ESP8266 is also hard to access and use. You must solder wires with the appropriate analog voltage to their pins for the simple tasks such as powering it on or sending a keystroke to the computer on the chip. You also have to program it in low-level machine instructions that can be interpreted by the chip hardware. This level of integration is not a problem using the ESP8266 as an embedded controller chip in mass-produced electronics, like the Arduino IDE. However, it is a huge burden for hobbyists, hackers, or students who want to experiment with it in their own IoT projects to create something new. But what about Arduino? The Arduino project created an open source hardware design and software SDK for their versatile IoT controller. Similar to the NodeMCU, the Arduino hardware is a microcontroller board with a USB connector, LED lights, and standard data pins. It also defines standard interfaces to interact with sensors or other boards. But unlike the NodeMCU, the Arduino board can have different types of CPU chips, which can be ARM or Intel x86 chips. These also contain memory chips and have a variety of programming environments. There is also an Arduino reference design for the ESP8266. However, the flexibility of an Arduino chip also means significant variations across different vendors. For example, most Arduino boards do not have Wi-Fi capabilities, and some even have a serial data port instead of a USB port. So, the question persists: why would you choose to use a NodeMCU when the more widely documented Arduino is around? Well, the NodeMCU has several distinct advantages. Before we detail them, however, we should state that the NodeMCU technically isn't a device, but rather the firmware that loads onto one. In practice, you'll see the NodeMCU firmware available for sale preloaded onto the board. If you already have an ESP8266, all of the connectivity options we'll run through here will still apply. There have been many different ESP modules over the years, each with their own advantages and drawbacks. There have been just two types of NodeMCU boards, however, version 0.9 and 1.0. The 0.9 version is blue and comes loaded with the ESP12 chip, while the 1.0 is black and comes with the ESP12E, which stands for Enhanced. There are several key differences between the two chips, the most notable being that the later one just comes with 22 pins and the early one comes with just 16. Given that the ESP8266 is more recent release than the Arduino, It's not surprising that it has stronger specs. There's a 32-bit RISC processor clocked at 80 MHz, along with a generous RAM complement and support for up to 16 MB of external flash storage. The device is especially useful for IoT applications thanks to its tiny footprint and built-in Wi-Fi support. In all other aspects, however, the ESP is pretty much similar to the Arduino. There's an onboard voltage regulator that ensures the cleanest possible power to the MCU itself, as well as a push button reset and a USB connection for easy interface with your computer, as well as serial transmission, which we'll get to later. The ESP8266 works with 3.3 volts rather than the 5 used on most Arduino units. To save space, there's no independent socket for a power supply. Rather, the unit is powered via a micro USB cable and provides 3.3 volts to the other components via 3 pins evenly spaced out around the edge of the unit. There are also 4 pins going to the ground. We suggest tethering your 3.3 volt and ground pins to the outer rails on your breadboard. It'll make life much easier as you design your circuit. Before we go further, it is essential for us to have an understanding of the pin layout, so let's quickly take a look at that. While the ESP8266 is often used as a dumb serial to Wi-Fi bridge, it's a very powerful microcontroller on its own. In this chapter, we'll also take a look at the non-Wi-Fi specific functions of the ESP8266. First, let's talk about digital input and output. Just like a normal Arduino, the ESP8266 has digital input-output pins which can be called I/O or GPIO. As the name implies, they can be used as digital inputs to read a digital voltage or as digital outputs to output either 0 volt or 3.3 volt current. Next, let's move on to voltage and current restrictions. The ESP8266 is a 3.3 volt microcontroller, so its I/O operates at 3.3 volts as well. The pins are not 5 volt tolerant. Applying more than 3.6 volts on any pin will kill the chip. Also, the maximum current that can be drawn from a single GPIO pin is 12 milliamps. Now, let's talk about the usable pins. The ESP8266 has 17 GPIO pins, which are numbered from 0 to 16. However, you can only use 11 of them, because 6 pins, GPIO 6 to 11, are used to collect the flash memory chip. This is the small 8-legged chip right next to the ESP8266. If you try to use one of these pins, you might crash your program. GPIO 1 and 3 are used as the TX and RX pin of the hardware serial port. So, in most cases, you can't use them as normal input-output while sending or receiving serial data. Analyze the board diagram on the screen right now. You need to be familiar with the majority of pin names, as they are bound to be used, sooner or later. To get the NodeMCU to read an analog voltage like the one produced by a moisture sensor or a potentiometer, you'll need to connect the signal to the ADC pin. This pin is connected to a device called an analog to digital converter, which, you've guessed it, will turn an analog voltage into a digital value that your microcontroller can make sense of. ADCs work by placing a row of comparators in series. If the voltage is read higher than a fixed voltage, a 1 will be output, while if it's lower, a 0 will be output. On the ESP8266, the ADC is 10-bit, which means we have 10 zeros and ones for a total of 1024 possible values. This makes it possible to record precise changes in voltage. For example, we might connect a rotary potentiometer to the 3.3 volt pin, the ground pin, and the ADC. Then, we turn the potentiometer to increase or decrease the value. You might think that having just a single ADC input on the NodeMCU would be a little bit limiting. And you'd be right. But happily, there's a device that can solve this problem, expanding that single input into 8 or more of them. The divisor is called a multiplexer or MUX. When you add the NodeMCU into your circuit on the app alongside the multiple analog input devices, a 74HC4051 multiplexer will be added automatically. Now, don't get intimidated by the numbers, it's just there to specify the model. So, let's go into a bit more detail about the different pins and communication protocols supported by the NodeMCU. Now, let's move on to the PWM pins. You'll notice that some of the digital pins come with this pulse width modulation or PWM functionality. This provides us with a means of simulating an analog signal using a rapid series of digital pulses. The longer the on portion of these cycles, the stronger the signal will appear to be. So, if you're turning an LED on and off rapidly, the longer the on cycle is, the brighter the LED will appear to be. PWM signals are also commonly used to control motors. The higher the PWM function, more power will be transmitted to the motor. You could do this using any of the digital outputs on the MCU by writing a cycle of code that rapidly cycles a given pin on and off, but this would interfere with the main program and use up many valuable resources, including, most importantly, energy. A better solution is to use one of the separate PWM outputs, which will take care of all the cycling for you once they've received a value. You can write to a PWM using the analog write function. Make sure that you've selected a PWM compatible output. On the NodeMCU, these are D2, D5, D6, and D8. That concludes the discussion about the hardware and pin modes of the NodeMCU. To finish off with this video, let's take a look at some of the major things you can do with an ESP8266 board. We can use it for something as crazy as geolocation. This is possible with Google's geolocation API. Google provides an API for taking data from our nearby Wi-Fi routers and giving us our coordinates. We can also build a wireless web server with the ESP8266. Next, we can also create an air pollution meter by interfacing the NodeMCU with pollution sensors and an application known as Blink, which acts as a database. In short, anything that requires data transmission over the internet begs the use of a NodeMCU, at least on a small scale. We will explore how you can use the Arduino IDE itself to set up the NodeMCU and program it in the next video, so be sure to watch it. Until then, bye.